My name is Armando,
I'm Amira.
I'm Jasmine. And I'm Grayson.
and we're the low-cost oxygen concentrator team at Florida Tech, graduating at 2021.
Currently, there are over 1.5 million Americans in need of supplemental oxygen due to respiratory diseases that cause low blood oxygen levels. Oxygen concentrators are a common form of treatment for these conditions. Currently, oxygen concentrators sell for around $1,500 to $3,500, making them out of reach for a large amount of the population. Our team works to develop a fully functional, low-cost oxygen concentrator to give people access to the treatment they need, regardless of their economic standing.
In order to develop our design, our team followed the guidelines from the WHO, which are the following: an oxygen concentration at least of 82%, a weight below 5 kilograms, a flow rate of at least half a liter per minute, and no bigger than an average backpack. It was also one of our main objectives to have a price below $800. In order to design our device, we divided it into three main subsystems, which were the pressure system, the mechanical system, and the electrical system. The electrical system included an Arduino IDE Mega 2560, a relay module, jump wires, and a 12-volt battery. The pressurized system included the seabeds, the surge tank, as well as the valve system and the compressor. We're using a dual head compressor in order to facilitate the pressure vacuum system required for our device.
When the user powers on the device, the battery activates the compressor to begin the first cycle. Ambient air is brought into the compressor through the first valve and then through seabed 1 to have the nitrogen absorbed into the zeolite. From there, the concentrated air is pushed out through the second valve into the back pressure regulator and then through the surge tank. From the surge tank, it's pushed through an outlet filter, through the flow meter, and finally out to the patient. Simultaneous to the oxygen absorption cycle, the zeolite regeneration cycle occurs. The compressor works to create a vacuum on one half of the concentrator while pushing air through the other half of the concentrator, ensuring the patient always has a continuous flow of air. As the compressor switches to a vacuum, the zeolite within seabed 2 regenerates by releasing the absorbed nitrogen. This nitrogen-rich air is then pushed through valve 4, through the compressor, and out through the purge vent.
The analysis of the device is classified under the testing, and it's split into two: the analysis of the final solution and the analysis of the actualized device. The analysis of the theoretical device or final solution consisted of performing different types of analysis on different parts of the device, the structural system and the pressure system. A finite element analysis was performed with respect to the pressurization of the polycarbonate cylinders during the PVSA system, and a force distribution analysis was also done on the device to make sure it holds with the structural system. The variable cost came out to be $866, and the final cost of the device was $900. The selling point would put it at $1,000. It would still be below the average cost of an oxygen concentrator already on the market. However, it would still satisfy the condition of being a low-cost oxygen concentrator.
For future work of our device, we would use a more efficient compressor and a longer lasting power source. Upon achieving the basic functions of our device, we plan on moving on to a renewable energy source, which would allow access to not only first world users, but to third world countries as well. So for our structural system, we have the base, which is a wood base, and then we have the brackets, which are the white structures right here, and these hold the welded metal plate, which supports all of the components upright. And in the back here, we were going to attach straps. So where the welded metal plate is, we would have holes, and then we would have use clips to attach the straps. And this would have been the back, which would have leaned against the person's back, and then this would have been the front, where they could connect their tubing to their nose, to the cannula, and then control the flow rate with the flow meter. To turn the device on, we hit the on switch, and this is the device working.